that's going to address the topic of the implications of truck platoons for roadside and vehicle safety hardware. We have two speakers today that worked on the project. It's Chiara Dobrovolny and Costin Ontario. Chiara is a research scientist at the Roadside Safety and Physical Security Division at TTI. She holds laurea in aerospace engineering from Politecnico of Milan, Italy, and a PhD in civil engineering from Worcester Polytechnic Institute. Dr. Dobrovolny directs research for various state departments of transportation, Federal Highway Administration, and University Transportation Center that design and test roadway safety hardware to improve the safety of transportation. These projects have used finite element computer modeling, statistical evaluation, full-scale crash testing, and benefit cost analysis to develop to improve roadside hardware and installation practices aimed at improving roadside safety. And Dr. Costin Ontario is an associate professor in the Department of Biomedical Engineering and Mechanics at the Center for Injury Biomechanics at Virginia Tech since 2011. Prior to that, he worked at the Center for Applied Biomechanics in the University of Virginia, where he received his PhD degree in 2005. His research interests include computational biomechanics, optimization, and material characterization. He has published over 200 peer-reviewed journal articles and conference papers. He has also led over 20 grants in the field of impact biomechanics related to the response of humans to impacts in automotive accidents, aerospace, sports, and military. His research was sponsored by industry, government agencies, including the US DOT, NHTSA, DOD, etc. He is an ASME fellow since 2017. So with that, I'll have our speakers go ahead and begin with their talk. And I think we have Chiara starting off. So Chiara, take it away.
Thank you very much, Michael. Thank you for the introduction. And again, welcome everyone. My name is Chiara Dobrovolny, and I will be hosting this presentation with Dr. Ontario. The way that we will present this project is with me starting with the implication of the truck platooning on roadside safety hardware from a hardware perspective, and then Dr. Ontario will take the lead and have discussions on his part of the work regarding occupant risk with use of instrumented dummies, all through computer simulation. So what is truck platooning? Most of you might be familiar with that or have heard about it, but truck platooning is an extension of cruise control and forward collision avoidance technology. It implies certain numbers of trucks that are really following each other, and they are following the lead truck. So the first truck will be manually driven, and the other are following wirelessly. Why would we look, or why would we want to have truck platooning? Is because it's considered as a potentially increasing fuel efficiency and also potentially increasing safety on our roadways. So the big question is, why do we need this research study? And what are the implications of this research study? Well, and we're talking about truck platooning, and we're talking about a certain number of heavy trucks, tractor trailers or tank trailers that are following each other on the roadway. We also know that on these roadways, we implement barriers, which could be median application barriers or roadside application barriers. Roadside barriers and median barriers are designed for a single impact. First of all, they are designed so that they should contain and redirect an errant vehicle for not only the safety of the occupants of the errant vehicle itself, but also for the safety of all other road users that are on the roadway at the moment of impact. These barriers are usually designed for a single impact, but at the same time, we do know that they are designed with a reserve capacity as a safety factor. So the big question is, due to the consideration they have a reserve capacity, do we think, can we prove whether existing roadside barriers might be adequate? And when I say roadside barriers, I really think about the rigid barriers. Are they adequate when truck platooning, for whatever reason, could potentially fail, and multiple trucks now impact the barriers really one after the other, so almost simultaneously? And if if that's true, so if these barriers are adequate, how many tractor impacts could I actually take without posing any risk to the occupants, but also to the other motorists? When we look at impacts between vehicles, so in this case, trucks and barriers, we also look at the ability of the barrier not only to contain and redirect the vehicle, but also for the vehicle to maintain stability throughout the impact event and after. So will the barrier prevent the impacting trucks to, from rolling over? And what are the associated occupant risks? So that's what we're trying to address through these research studies from computer simulations. So how did we develop this research study, especially considering this was a collaborative effort between the two institutions that have a very specific, expertise? The first step was to select representative barriers that we wanted to evaluate. Obviously looking to rigid barriers, concrete rigid barriers, and we specifically look into barriers types that had been crash tested and for which we have the data so that we can actually use it to validate our computer model system. You'll see that in a moment throughout my next slides. Then we had to develop computer models of these selected barriers, not only to replicate the shape and the general dimensions, but also to replicate the concrete properties, the reinforcement, and therefore replicating the strength of the barrier. We then, through computer simulation, we have then to go ahead and validate the model with the use of a tractor-trailer model with respect to an existing full-scale crash test for which we have data, so that we can make sure that our system, our FEA model, finite element model, is correctly replicating what happened during the impact. But the subsequent impacts from the other potential track platooning were predictive computer simulations. And we did a few more after the first one you see through the next slides again. When we ran the impacts for each one of these simulations, we did need to evaluate both the barrier adequacy to contain and redirect the vehicle, also its residual strength and the associated occupant risks, together with the vehicle stability. So this is a quick slide that shows the system that we have modeled. These are just a 3D rendering of our FEA models. So you can see the general shape of the two concrete barriers that we chosen, and the orangish lines represent basically the reinforcement of these systems. So there was a specific reason why we chose these two barriers. For number one, those were the two barriers for which we had crash data, and they had a very specific characteristics that appealed to us. The first one, which is the MANITOBA bridge rail, which is the one more on the bottom of the slide, is a little more than 49 inches tall barrier. It's a single slope shape and is a bridge rail. So the interesting part of that barrier is that we have to develop the model of the deck as well. Because during these impacts, if these barriers are connected or are implemented, as a bridge rail systems, we need to pay attention to what happened to the deck. We want to make sure that the deck wouldn't fail. The barrier might not fail, but if the deck does, that still would be a problem. And the second barrier that we'll look into is, which is on the top right of the slide, is a concrete medium barrier. And this barrier was interesting for us because it's a 42 inches tall barrier, which is really the minimum height that is required from a design and testing implementation rigid barrier for when we think of these tractor-trailer impact, following our roadside safety mesh standards. So that's why there were some of the reasons why we chose these two systems. This is a quick slide just to show the model of the vehicle that was used. It was a roughly 80,000 pounds tractor trailer with a 48 foot trailer long. And very important that I wanted to mention are the impact conditions that we use for these impacts. At the best, really the best of our knowledge at this point was to replicate these impacts following what the current standards for roadside safety barrier testing and evaluation criteria provides. Our manual for assessing safety hardware, which is called MESH, standard requires that when we design and test these type of roadside safety barriers, and they need to be evaluated according to impacts with tractor trailers. These tractor trailers need to impact the barrier at 50 miles per hour and 15-degree orientation angle between the truck and the barrier. So this is so the first few slides are going to be with respect to the MANITOBA barrier. On the left, in this slide, you have the crash test that was performed and that was provided by Midwest Roadside Safety Facility. And on the right, you see that what I called the validation simulation, which is the simulations that wants to replicate the impact of the crash test and is used to validate the model that is going to then be continuously used in the subsequent impacts. It might be hard to see, but you can see that there is some displacement of the barrier, which is going to end up in a small permanent displacement of the barrier. And there are going to be, I'll show you later in other slides, some minor spalling on the top of the concrete. But you can see that the model fairly good replicated the crash test. In fact, it was actually validated through the RSVVP program that we use for barrier design. The subsequent slides are going to be predictive simulations of the subsequent impacts. So this is the test number 2. This is the simulation or the impact number 2. So this will be the second truck that follows the first one. And after the first one moves away, then the second one comes and impacts the barrier. Now, the barrier has already, you can see, there is a preliminary displacement was maintained and also spalling from the previous test. And then throughout the second simulation, you can see that there is more spalling and more displacement of the barrier due to the second impact. Again, the truck stays upright and doesn't roll over. This is the third impact. And throughout these impacts, you'll see also in the next slides, you can notice there is a little more displacement, definitely more spalling on the barrier to the point that we're going to have actually exposure of rebars. And please also pay attention, this is the fourth truck coming up now, pay attention to how much the vehicle is rolling. So although the vehicle is being still contained and redirected, and it would pass all the criteria according to our mesh standards, we still have quite a bit of roll that is increasing more and more. And actually, by the way, in this simulation, which is the last one that we perform, you can see there is a considerable roll. But again, we have a good, this barrier was originally 49 inches tall. So even though we had lost some of the height of the barrier, and you can see actually in red there are some of the exposed rebars already, still the vehicle was able to be contained and redirected. So to basically show it, in this slide I want to show the barrier damage. This was from the first impact that actually, by the way, the test, when we validated the model, we also validated the model with respect to barrier damage. So this was also the type of damage that was observed during the test. But this was the amount of damage on the barrier that was observed during the last of the 5 impacts. And again, this is a predictive simulation, but that's what it would potentially represent the barrier after these continuous impacts after impacts. And again, the track platooning is very significant because it will be potentially, unless we have additional data that we can review, but potentially at the same location. So you're impacting the same location all over and over again. So a quick summary and, I guess, conclusion on the MANITOBA performance, it looks like the barrier was adequate for at least those 5 consecutive tractor-trailer impacts that we performed through computer simulations. And the impact tracks were stable throughout the impact event and even after, and there was no rollover that occurred. Again, Dr. Untaroy will talk about more in detail occupant risk after I complete this part of the presentation. However, we also have enmesh values to evaluate occupant risk, and there were no issues associated with that as well. So my second part of the presentation is regarding the concrete median barrier. So this is the test from Midwest Roadside Safety Facility that was performed, and this is the simulation that again was performed to validate the model against that test. And it's hard to compare when they have different speed, but you can see that it was actually validated as well in terms of performance. And so if we go to the next impacts, again, these slides want to show the second impacts, you can see that during the impacts of the subsequent trucks impacting the system, you will notice there is not as much, in this case, there is not as much lateral deformation, but you will notice more and more this erosion of the elements, which replicates the spalling of the concrete during the impact. For the concrete median barriers, we did perform 4 impacts with the tractor trailers. And again, this is the third one. Please keep noting also the behavior of the truck. And you can see also, this is the last simulation that we performed, that's the 4th truck impacting. You can see how the stability of the truck might become, of course, it might be, the vehicle may become more and more unstable. And in this specific case, if you recall at the beginning, I mentioned, is because now we are losing more and more the height, the effective height of the barrier. It was initially 42 inches, which was the minimum height that was required. But now, if we look at the damage of the barrier, so this is the damage of the first impact, again, validated against the test. But now we have the damage of the last impact. Now, we don't get into really exposing rebars as for the other models, but at the same time, please note how in the location of impact, which again for truck platooning is always the same, we have a reduction of the effective height. And so that would be a big question to consider when we design these barriers, if we keep in mind a potential truck platooning. So even in this case, for the concrete median barrier, the barrier adequately was able to contain and redirect the 4 consecutive tractor-trailer impacts. And all these impacts, in all these impacts, the truck was able to maintain a stability, although we saw some pretty accentuated rolling angle, but did not roll over, which is what we wanted to surely make sure it didn't happen. Couple of more slides to conclude, at least from this perspective, from the perspective of the barrier design itself. We can say that due to the impacts at these given conditions, we have a final deformation, final permanent deformation of these concrete barriers that was less than 3 inches for both of them. We didn't see the likelihood for a catastrophic failure during any of these impacts that happen in series into these barriers. Both the concrete MANITOBA bridge rails and the concrete median barrier are potentially capable of containing and redirecting multiple impacts at these mesh testable 5 impact conditions, the 50 miles an hour and 15-degree angle. And so it is assumed that other similar concrete barriers with a similar design capacity, that is very important, needs to have a similar design capacity, will show similar results. And then last but not least, we have a few recommendations. So we would recommend additional studies to identify potential impact conditions of these truck impacts. So we did use the mesh testable 5 conditions the 50 miles an hour and 15-degree impact, because we don't have any other data, or at least at the time of these of the conduction of these projects, we didn't have other data. But I surely would be very interested to understand what would be the potentially impact condition of these trucks. Would it be all the same, or would these trucks, for some reason, slow down or have a different impact angle, you know, when we go from the first one to the last truck? So that's really an unknown, at least from us, and that we think would be very valuable to investigate. We do also recommend at one point to be able to conduct crash testing on a potential truck platooning on rigid barriers, because we were able to validate the FEA model according to the crash test conducted, but that is really only the first impact. So we don't have other ways which would be very valuable to make sure that our predictive simulations are really accurate, especially when you're talking about 4 or 5 impacts consecutively. And also, we know that DOTs have different standards for minimum bridge deck depth. And so we would suggest that also the deck capacity would be verified, because you need to verify the adequacy of the deck capacity depending on the different deck depth. If a deck is 7 or 8 inches tall rather than 12, you know, the deck capacity could change depending, of course, on the type of reinforcement. And last but not least, I also wanted to add a comment that I mentioned before. You know, we look into, right now, we have a minimum height for these rigid barriers for testable 5 conditions, so by considering impacts by a tractor trailer vehicle, and that's 42 inches. But if we do anticipate potentially having multiple impacts that could potentially spall the concrete on the top and decrease the effective height of the barrier, maybe it would be a good idea to potentially consider increasing the minimum height of this barrier if we want to keep in mind the potential truck platooning impact. With that said, I have completed my part of the presentation, and I will stop sharing and having Dr. Untaroyo continue with his part of the presentation. Thank you very much.
Okay, thank you, Chiara. Dr. Ontario, I think we see your slides. Can't hear you yet, so if you're muted, probably want to come off of mute.
Okay, do you hear me now?
I do hear you now, yes.
By Chiara and her group in TTI. So in parallel with her group, we developed the cabin only. We took the cabin from this truck, which was used in crashing, and that cabin has no interior parts. So we have to take interior parts from literature, you know, the seat, you know, the other parts from the interior, and put in that cabin. And we also have to set up hybrid 3 and Tor occupant dummy in the cabin only. So this was in parallel. After that, we couple, you know, these 2 groups. So we got from TTI the nodal time history from some nodes from the cabin, and we apply here the motion to our cabin only model. In this way, we first, you know, was different problems here, because one thing, the track model was proprietary, it was TTI, so they cannot share. And the second, we also developed a model which was much computationally effective, because you know, we don't need to simulate with the whole track what we do every time when we run with our dummy models. Finally, we perform impact simulation with cabin-only model and seated dummies, and we evaluate occupant risk of injury and seat. We did also a sensitivity study where we changed the seat position. And of course, we evaluated again occupant risk of injury. This is a kind of big picture of our part. And now I will try to explain every step. Now, cabin only. We took, so it's the same cabin from the truck, and so has the same node number and everything. So we took, for example, 8 nodes, 2 from 4 from upper side and 4 on the floor. And we prescribe the motion of these 4 nodes. And we put also some boundary condition here in such a way to see if we can predict the same motion of the, we're interested more in the seat, right? Because we transfer the whole motion to the seat. And how we verify our model, we took another 4 nodes, which are not this, which is prescribed motion. And we compare what we got from this model, from cabin only, with the full model, with the truck. And here we found small differences. I think I remember 3 or 4% maximum in displacement. So this gave us some confidence that our cabin model, you know, move in the same way like full truck. After we this, we move to put dummy in the seat. We start with a hybrid 3 dummy model. This model was developed by LSTC, is a company who, software company who developed also LS-DYNA program, which was used in by both groups in TTI and Virginia Tech. And we also develop, you know, this belt system, restraint system, and so on. Here we had also some our tested in our lab for belts. So we put a material property from our test to be sure that they are realistic. And we start to run simulation with this model. So this is hybrid 3. Another model, we use TOR dummy model. TOR dummy model, you know, needs considered to replace at some point hybrid 3 with TOR dummy. It's a dummy more advanced than hybrid 3, is more biofidelic and so on. And we work in the past with NHTSA different project, but we also work with NASA. Another project, which here you see Putman and all, it's the work from NASA. So it needs a model, but it's also some improvement from Virginia Tech from the project we work with NASA. With NASA, we run in different conditions than NHTSA. This was for especially for aerospace. So you know, theoretically, it should be better than NHTSA model. And here, occupant, how we assessed the injury of the based on dummy. So we use 4 criteria. We use for injury for head. This is well known. It's HIC. You know, it's based on acceleration of center of gravity of the head. NIG. It's based on the forces in the neck and chest, the deformation, deflection of chest, and femur, the force in the low cell in the femur. And this is, data injury criteria here. It was developed in literature we took from Yogananda in 2015. The probability of injuries. There is this function where actually you introduce HIC and you calculate, for example, how much is probability to have head injury, for example. So this is injury of certain, body parts, right? Head, neck, chest, and femur. But in order to compare, the different condition, we have to combine all in a number, and we call this occupant injury measure. And there is, it was proposed, for example, this formula by a group, Crash Avoidance Metrics Partnership Advanced Distance System CAMP project. And so we use this formula from that project. So this is the probability of injury of IAS 3+. IAS 3+ injury means serious injuries. IAS, it's again, it's abbreviated injury scale. It was created by Association for Advance of Automobile Medicine, and give you a kind of an injury risk based on what you measure on the dummy. So in terms of kinematics, you see that this is a different times. So this was with the first track. We have many simulations. I try to extract some of them. And so you see here hybrid C compared with store. At the beginning, they are somehow similar, but there are also some differences, especially when you move to, for example, 0.5, 0.6, and so on. So this makes sense because they're different models. In terms of injury, you don't see so many differences, actually. You see, for example, then in head, we have very low probability of injury. I put here only first and fifth impact, the first and the last impact. And the highest injury appear actually in the neck, but still it's very low. It's under 10% probability. So, and also in chest a little bit, 3 or 4% in hybrid 3, but not much in TOR. But anyway, this is the probability of serious injury is very, very low. This we can say here. So this was with MANITOBA concrete bridge rail impact. Here we calculated also OIM for this. Again, you see on OIM, you see actually not big difference between these two. You see hybrid 3 in first impact is 12, with story it's 11, which means that actually, both dummy are effective and there is not big difference. See, this also gives us, more confidence because, if you run with one dummy, maybe you say maybe the problem is with that dummy, but when you run with 2 and you get the similar results, means that, you're more confident. The OEM value anyways, under 15%, which correspond to relatively low injury risk for occupants. So it seems that, it's not high risk for injury. The same was with concrete median barrier. I don't know why my boxes are not in the right place, but anyway, you see somehow similar, which what we saw in MANITOBA barrier. So the value are not far away, but here it seems that to be a little bit smaller, but anyway, they're very, very small injury risk. And you see the same trend. In neck, you have higher probability of injury. You don't have in head almost nothing, and a little bit in chest for hybrid 3, but femur under 1%. So again, you can say that the probability of injury is very small. The same in OIM. So when you put all together, all injury for body regions. So again, you see that hybrid 3 predict about 11-12%, and TOR about 9-10%. This is a very low injury. So what you can see, hybrid 3 actually is predict higher, a little bit higher than TOR. Usually I see in other simulation, in other tests, different. Usually TOR predicts higher than hybrid 3, but here it's more, I think, related to the sliding of the belt on the chest than other stuff. Because anyway, both are very small, so you cannot say too much. Regarding, it was also a discussion on what's happened, for example, when the driver will not stay in the same position, because we talk about automatic driving. So probably the guy will not stay on the steering wheel, but probably will not have steering wheels. So what's happened when the driver stay in different angles? And this is a big question right now also with other car, you know, it's sedan and SUV, not trucks. What's happened when the seat is rotated with different angles? So we place this with hybrid 3 here. So we move a little bit, you know, the seat from where it was at the beginning, and in order to have space here. And we rotated the dummy with 15%, with 30%, 45%, and 60% from traditional seat, you know, 0 degree, sorry. So, and we wanted to see what's happened. And here, for example, for 15-degree rotation, seat angle, you see, for example, from 0 seconds, 0.9 seconds, 0.13, 0.18, actually, you know, the shoulder belt is moving completely from the chest. And so this you can see, it's a kind of, and this we saw also in another, with sedan stuff, what we run in different, in other project. It's when you change the rotate the seat, you may have the problem with the belt, because the belt will slip from the dummy. So, and here you see, for example, kinematics, a different for a seat at different angles, at 15%, 30, 45, and 60. It seems that the worst was 15 degree. 60 and 30 was probably better, and 45 and 60 also. But if you look on numbers, they're pretty small, so you cannot see too much differences. For example, you know, it's somehow similar, between 6 and 8% in neck, and in chest it's between 4 and 6% injury. In head and femur, almost always under 1%, a little bit here above, but this is not important. So, you know, the take-home message is this, you know, the injury, it's lower. And if you have the kind of risk of injury, it's only neck. And if you go to see the whole occupant injury risk for the whole dummy rotating seat, you see the number not different, about between 11 and 13–14%. So even with rotating seat relative to the truck, the occupant injury risk remain low. So the last part, the last slide, it's a kind of conclusion. Some of the conclusion were also mentioned by Chiara. So it's in this mesh condition, you know, the MANITOBA bridge and concrete bridge were impacted by 5 tractor van trailer models, and we didn't see any catastrophic failure. We saw also low injury risk in OA, for example, OIM was under 15%. And this means that the barrier design can be considered effective in protecting belted vehicle occupant in platoons. Regarding recommendation, you know, we use now dummies, but probably was better to use human body model. And right now, we have global human model, for example, human model, which can put in this configuration and run and see more specific is, you know, what kind of injury will appear. Another thing, we consider only 50% male. So what's happened, for example, if driver has different anthropometry, again, this can be done with different models, with female model 50% with 95% male, and so on. But I don't expect too much differences. You know, probably, you know, the small female will have higher injury risk, and big guy will have lower, but not, you know, between this, what we saw, 12–13%. So probably this we can expect. So this is all. So this is, you know, if you have any question or whatever, you can contact us, Dr. Chiara Dobrovolny, and I post my email. So this is all. Thank you.
Very good. Thank you, Kostin. I appreciate that. And Chiara. I guess at this time we would open up for questions from anybody.
Yeah, I'm kind of curious, guys. You know, the barriers you tested are, I would generally consider to be pretty robust. Do you think it is worth experimenting on the more lightweight guardrail systems that we commonly see, you know, outside of sort of bridges? And may also, you know, bridges have a very obvious significant hazard, but sometimes the more lightweight steel based systems are, you know, either near sharp edges or against cliffs and other potential hazards. So I'm kind of curious your thoughts if they'd have an equal level of success at multiple strikes from a string of heavy tractors, or if you expect maybe a lot different outcome.
Sure, I can speak for that. Can you hear me?
Yes.
Yes, sure can.
Okay, good. Well, a couple of comments, actually. That's an interesting question that you brought up. So I just want to make sure that when we talk about, you know, steel systems, we do not consider the commonly known, I guess, post and beam, double beam guardrail system. That would not be able to sustain the impact of the SUT of the heavy truck. This is generally guardrail of that types are more for passenger vehicle impacts. Maybe potentially get up to at one point to a little heavier vehicles, but not the tractor trailers. I think what probably you were referring to mostly could be system like a bridge rail, so that might have either combination between concrete and steel material. Some of these bridge rails might be just a steel material, not steel, but, you know, in general metal material. Well, definitely at that point, you probably would have to perform a investigation, separate investigation for those systems. Like I mentioned at the beginning of the presentation in my slides, DOTs have a different type of barriers, even just the simple concrete barrier. Even if they have the same shape and the same height, the reinforcement might be different. So you really need to give consideration to, if you have a barrier that has some components of concrete, you need to look into the reinforcement to define the strength. But if you don't have the concrete and you have the metal, you know, whatever that could be, generally steel, you need to make sure that it's properly designed to, you know, have an adequate strength. The strength is only one of the aspects. As you pointed out, there could be other relevant aspects, such as splices between these metal elements, which could be a potential for snagging. But like I said, it really would have to be, you know, I'm not saying every single potential variation would have to be investigated, but at least identified, you know, some categories and look at, you know, the one that might be considered less strong from a strength perspective, and then maybe go from there.
Great, yeah, that helps me out a lot. Appreciate it.
Absolutely.
Okay, well, I think that wraps up, I guess, the webinar for today with no more questions. I really appreciate your time and really interesting topic, and love the simulation stuff. It's pretty cool to see. Anyway, thanks so much, and thanks everybody for participating.